Okay, so just a quick recap. What we said was that when a synapse, so when the beginning of the axon is stimulated, and we'll come back to the detail of the events that happen here, some sodium comes in. When some sodium comes in, it opens voltage-gated sodium channels and causes a lot of sodium to come in. And because of that, we start to get depolarization here. Okay, so the resting potential starts to become a bit, you start to get higher than the resting potential of -70 starts to go up because sodium's coming in. When enough sodium comes in here, you open enough voltage-gated sodium channels to reach the action potential of around +40. And that is when you start to get repolarization happening, because the voltage-gated sodium channels have closed and the voltage-gated potassium channels have opened, and so the potassium is now going out. It overshoots by a little bit, which causes the voltage-gated potassium channels to close. At the point where you have both the voltage-gated sodium and the voltage-gated potassium channels closed because of the voltage, at that point the sodium-potassium pump continues its work and brings the potential back to resting potential. Right, and now what we'll just quickly discuss is how does movement of this impulse, so the impulse has happened here, how does it move? Well, when the sodium comes in, it can diffuse in both directions, and so when it diffuses, it's going to affect the voltage-gated sodium channels in the neighboring area, and so it's going to open those voltage-gated sodium channels and cause sodium to come in here. When sodium comes in here, again, it can diffuse in both directions. When it diffuses that way, it can open the voltage-gated sodium channels in the neighboring area, and so sodium comes in here, and when sodium comes in there, it can diffuse in both directions and open the voltage-gated sodium channels in the next area, and so the events of the action potential are kind of propagated along the axon. One of the things that comes up often is, why does the impulse move in that direction? If the sodium comes in and can diffuse in both directions, why doesn't the impulse kind of move in both directions? And the reason for that is, while you have voltage-gated sodium channels here and you have voltage-gated sodium channels here, these ones have recently opened, and because they've just kind of recently opened and then closed because of the events of the repolarization, once they are closed, they go through a period a period of time that is known as the refractory period. In this time, even if some depolarization is experienced by this channel, if it's in its refractory period following a recent action potential, it will not respond by opening during the refractory period. However, this one that has not recently undergone an action potential, this one can open, and so even though the sodium diffuses in both directions, when it comes in, it's only going to open this one, and so the action potential will only be propagated in one direction. Okay, so that's the first thing about the propagation of the signal, right? And remember this, we could be talking about a sensory neuron, we could be talking about a relay neuron, we could be talking about an effector neuron. It's just about how that impulse moves along and what the nature of that impulse is. Now, the next thing we're going to look at is speed of conduction. So we've looked at the directionality of that conduction. We've looked at what the reason is for why it only moves in one direction. The next thing is speed. So we looked at directionality, now the next thing is we're going to look at speed. And you should know where I'm going with this. you can, by having the Schwann cells, so we've kind of cut them in half here, but these are cells that have wrapped themselves around parts of the axon called Schwann cells, and their layers of phospholipid that makes up the membrane provides a lot of insulation to the cell in terms of wherever the Schwann cells are, the ions can't really move. So the sodium moving and the potassium movement across the membrane can't really happen in these areas. They are effectively electrically insulated. And so when you do have Schwann cells on an axon, i.e. this axon is myelinated, if you do have a myelinated axon, what that means is that the events of the action potential are concentrated at these non-myelinated areas known as nodes of Ranvier. And for our purposes right now, and because I kind of don't fully understand why this is, but it suffices to say that because the events of the action potential and because the ionic movements and the depolarizations are localized to the nodes of Ranvier, because of that, the action potential effectively, instead of moving along like we just discussed previously, gradually along the axon, instead of that, it has to jump from node of Ranvier to node of Ranvier, effectively speeding up the conduction of the action potential. Okay, so that is speed of conduction. Now what we'll do, and while we're here, we'll just kind of make sure that we understand the events of the action potential by just looking at this. So when this area is undergoing, so the depolarization here has caused, the action potential here has caused the depolarization here. Okay, so here we might be looking at a place that is just beginning to depolarize.